Hello friends, in this video I'd like to solve the following problem from the Romanian National Mathematical Olympiad for 12th graders, year 1996, problem number 3. Let A be a commutative unital ring such that for every non-zero element A of our ring, there are positive integers m and n satisfying A equals a to the power of m plus 1 all to the power of n. We wish to show that every endomorphism of this ring is actually an automorphism. It's a beautiful algebraic problem. Here are my hints. First, this well-known lemma, which I will prove because the proof is very quick. If f is a field in which 0 is not equal 1, then any endomorphism H is injective. Any endomorphism is automatically an injection when dealing with fields. Then, you should be able to show that A is in fact a field, which means that for every non-zero element of this ring, it has its inverse. So there is B such that AB equals 1. And to show that, the binomial theorem will be useful. X plus y to the power of n equals the sum as k goes from 0 to n choose k, x to the power of k times y to the power n minus k. We know that the binomial theorem holds for complex numbers, but in fact it holds for any commutative ring with unital ring. Now, to show that any endomorphism H is surjective, this is the hard part. Fix any element A of our ring and suppose that a to the power of m plus 1 all to the power of n equals a. And consider this polynomial p of x equals x to the power of m plus 1 all to the power of n minus x. Let u of p be the set of roots of this polynomial. Notice that since a is a field, the set of roots of polynomial in one variable is finite. There is only at the most m times n roots of this polynomial, at most. Now, show that our endomorphism H takes the set of roots into itself. And since this set is finite and H is an injection, we know that any injection from a finite set into itself is a bijection. In particular, any root can be written as H of some other root. And that should be enough. So give this problem a try. You know what, let's start with proving this lemma, because proof is very quick. Proof. Suppose to the contrary. Let's suppose to the contrary that our function, our endomorphism is not injective. That H is not injective. i.e., which means that H of some element is 0 for some not zero element A. But notice that then we have the following problem. Well, 1 can be written as H of 1, but H of 1 is H of A times A inverse. Because we assume that F is a field, A is not 0, so it has its inverse. But notice that H of A times H times A inverse is H of A inverse. But H of A is supposed to be 0. So we have a problem because it's 0 times something is 0. And now we have this problematic equation, 1 equals 0. We are supposing that this is not the case. So it's a contradiction. Very quick contradiction. Very quick contradiction, which closes the proof of my little lemma. Alright. Now, for the actual problem. I will proceed by proving few claims. Claim number 1, I claim that A is a field. Claim that A is a field. Proof. Proof is very simple. Maybe not so simple, sorry. Let A be some element of our ring, but let it be not 0. Notice that by assumption, we know that there are m and n positive integers such that a to the power of m plus 1 all to the power of n equals a. And now what I will do, I will take this left-hand side and I will expand it using the binomial theorem. So the left-hand side can be written as sum as k goes from 0 to n of n choose k, a to the power km, well, times 1 to some power, but doesn't matter. All right, and now what I will do, I will leave the first term where k equals 0 on the left-hand side, and everything else will be put on the right-hand side. If k equals 0, then I have just 1. 1 equals a minus the sum as k goes from 1 to n choose k, a to the power km. And finally, I will factor out a right here. N choose k, a to the power km minus 1. Notice that the exponent right here is still greater than 0. It's still greater than 0. All right, which means exactly that our greater than or equal 0 doesn't really matter. Notice that means that our element a is invertible, because a times this element is 1. A is invertible. And that closes this proof of this claim, because this means that our ring A is a field, because every non-zero element is invertible. By the way, I am assuming that in this unital ring, 0 is not equal 1. If 0 equals 1, well, this theorem is then trivial, because the only endomorphism from set having one element is, well, itself. So it's obviously a bijection. So I am supposing that it is not 0 is not equal 1. All right. So we know that our function is a field, and as an immediate corollary of this is that h going from A to A is injective. It is injective. Any endomorphism. Maybe let's write it that any endomorphism. Any endomorphism H is injective. All right. But now the harder part is to prove that it is surjective. So my claim number 2 and final, claim number 2, I claim that H is surjective. And it is harder to prove it. Well, proof. So let A be any element of our ring, any element whatsoever, non-zero, because we know that 0 is mapped to 0. Let's concentrate on A, which is not 0. Well, then, notice that then a to the power of n plus 1 to the power of n equals, well, again a, for some positive integers m and n. All right. Now, crucially, let's consider this polynomial. P of x is by definition x to the power of m plus 1 to the power of n minus x. And let u of p be the set of elements, the set of roots of our polynomial p. The set of all elements such that p of this element is 0. Well, notice the following. First, since our ring A is a field, well, what then? The set of all these roots must be finite. The cardinality maybe just u of p, up is finite, which is very important. Moreover, let's see. So let's suppose let u be in our set up, i.e. U to the power of m plus 1 to the power of n minus u, let it be equal 0. What happens if I apply function h to u? Well, let's see. What is h of u to the power of m plus 1 to the power of n minus h of u? Well, let's investigate it. Since h is an endomorphism, h of u to the power of m is the same as h of u to the power of m plus 1 to the power of n minus h of u. Well, but h of u, notice that 1 is h of 1. Maybe let's write it. So we have h of u to the power of m plus 1 to the power of n minus h of u. But again, multiplication, we can take this exponent inside. And using once again the fact that our function is endomorphism, we have this. All right, and it is h of 0, of course. And h of 0 is 0. So our function, image of every root is again a root, which means that h maps the set of roots into itself. Yes, because every root is mapped to another root. And now, crucially, since u of p is finite and h is injective, h must be even bijective. Yes, well-known property of finite sets. In fact, this property characterizes finite sets, that every injection is automatically a bijection. That means that this element a, which is a root, is h of u for some element u of our ring, which means that our function is surjective, which closes our proof. Yes, because we have demonstrated that every element can be written as h of u. So our function is surjective. So it's injective, surjective, so it is bijective on the whole ring, which means that, of course, it's an automorphism. It's an automorphism. And again, one more thing before we go. Notice that I have assumed that in this ring A, from the beginning, I have assumed that 0 is not equal 1. Well, if 0 equals 1, you have trivial ring with one element, and you can verify it easily that, well, there is only one function which maps 0 to 0, and this is obviously a bijection. Yes. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.